This video will demonstrate one example of using Python scripting inside of a Psi4 input file. So I'm at psicode.org. I'm going to go to the user manual. I'm going to go to Psi4 tutorial, potential surface scans, and counterpoise correction made easy with Psithon. So Psithon is the name for the kind of special version of Python, of the Python programming language we use within Psi4, such that you can treat a Psi4 input file like it's a Python script and do any kind of scripting you would do with Python inside of a Psi4 input file. So this is the input file that I'm going to be using here that I've copied down verbatim in demo5.in. Okay, so this is an example potential energy surface scan and counterpoise correction for the neon dimer. Okay, so let's see what's different about this relative to our regular input file. I have memory of 250 megabytes, declaring the molecule. I've named the molecule dimer. In this case, naming the molecule, I believe, is necessary for what we're going to do later on. I have neon atom 1. I haven't declared charge and multiplicity, because if you don't declare that in Psi4, it'll assume neutral singlet by default. It'll assume charge of 0 and multiplicity of 1. Then another neon atom, it's bonded to neon 1 with bond length R. And notice we haven't declared R yet, what it is. Now I have a Python array called rvals that has values 2.5, 3.0, and 4.0. So that part is Python. I'm going to set my basis set to augccpvdz, the augmented double zeta Dunning set. I'm going to set the keyword freeze core to the value of true. So that's going to set that keyword to true. And then this comment here lets me know that this ECP here, open brace, close brace, that's initializing a blank Python dictionary that we're going to put some values in later. So this is particular to Psithon, that we need this particular syntax for what we're going to do below to work. Okay, then we do a Python loop for R in rvals, in our array rvals, so all the entries inside of there. We have dimer.r, that's our molecule, and the value R for our dimer is equal to R, the value we get from the array rvals, looping over all three values inside there. Then we set the counterpoise corrected energy, this ECP dictionary that we declared. The value R in that is equal to, then we're calling the function CP for couple cluster, singles, doubles, and perturbative triples. So CP is like energy, except what it's going to do is it's going to compute the energy of the dimer, then subtract out the energy of each of the monomers. And it's going to do that in the dimer basis set. So this will give us an interaction energy, how strongly these two neon atoms prefer to interact at those distances. Again, all these distances are in angstroms. So once that's done, we'll have those energy values inside of this array. And then finally, we're going to print out some values. So in order to use the Python print function in Psithon, we need to do this type of thing, psi4.printout. Then that works just like a print statement inside of Python 3, where you have the parentheses and the print. So new line, declaring a header for this table, and then what the values in this table are, and then kind of a line breaking up our table. Then again, we have a Python loop for all the R values inside of rvals that are now inside this array. The value E equals our energy times psi Hartree to kcal per mole. So that's going to convert these energies from being in Hartrees to being in kilocalories per mole. And then we're going to print out the values, print it out in this floating point format for the value of R and for the value of the energy. Okay, so let's see this in action. So I've got demo5 was that input file name. I've got Psi4 in my path. We're ready to go. Making sure I have my scratch set, which I do. So I'm going to do Psi4, let's see, demo5.in -n4, and then maybe I can create a log file as well, demo.in demo5.log if I want. Okay, now I'm going to tail my output file, demo5.out. It's running all those couple cluster jobs. And now the nice thing is that when it's finished, we have our Psi4 exiting successfully, so we know we completed without errors. When it finished, it prints out those values we had at the end of the input file. So this is that table, printing out the R values in angstroms that we had in our original array, and the counterpoise corrected CCSD parentheses T aug.dz interaction energies that we had at those distances. So positive 0.75, 0.01, and minus 0.01 kilocalories per mole. So this is a really nice thing with Psithon and using Python inside of Psi4 input files, is that we can take things that would be the work of multiple input files and then perhaps another script to be able to print out these nice formatted tables. Those kinds of things can be automated and made a lot easier in Psi4. We can do the same kind of things with other keywords like the basis set or what method we're using, whether that could be Hartree-Fock, MP2, etc. Whether that basis set could be, say, 631G star, STO3G, CCPVTZ, whatever we like. So a lot of this work, which could be tedious work on its own, can be automated and made a lot simpler using this type of scripting within the Psi4 input file.